So we'll have these 5 problems. Problem number 1 will have between 4 and 5 parts, so A, B, C, D, or A, B, C, D, E. Problem number 2 will probably have 2 parts. 3 will probably, the rest of them will probably each have 2 parts. So.
I'm not sure if I can answer this, but for the short answer problem, would that be like explaining like what a theorem is, or like?
I think it could vary. So it might be explaining a theorem or how to use something.
Or like what's going on in spring problems or something like that?
No.
Not so much.
So I think I'm going to restrict the spring problem to just the last problem. So I probably won't be asking too many spring problems in problem number 1. The kinds of questions that would come up with number 1 would be kind of like similar to the review, and we'll take a look at the review in a few minutes. So maybe I should just put answer problems instead of short. Not so short answers. Put the not so in parentheses. Yeah. Not a comprehensive test. No, because so the first test kind of focused on first order differential equations, and I don't think we're going to have any of those types of problems here. Yeah. Okay. Yeah, so the initial value, there might be the homogeneous and non-homogeneous might have initial value problems associated with them. Probably, yeah.
Can we use a calculator? Yes, right?
Calculators. Okay. The thing about calculators is that the TI-89 can actually solve differential equations. So.
If I can't use my calculator, I'll do a quadratic formula.
Okay. Okay. So, okay. Okay. All right. So you will be allowed to use your calculators. Yes. You can use your calculators. Any other questions? Yes.
What section should we review?
Okay.
Can we go over like variations of parameters
That's the one with the last one.
We know not variation, I mean like undetermined coefficients.
And so we'll do some undetermined coefficients in spring. Okay, so first of all, what's going to be covered in the test? So chapter 4, except the last 2 sections, 4.9 and 4.10. If you want, I didn't talk about that at all. So, okay. All right, so the test will cover all of Chapter 4 except for the last 2 sections in Chapter 4, and then it'll cover Section 5.1. Okay?
I'm sorry, 5.1, just the simple harmonic motion, or do you want to?
Everything in 5.1, including the damped and undamped and stuff. 4.9 and 4.10. So 4.9 and 4.10 will not be covered. Oh, 4.7, which is the annihilator method.
So gravity is what do you
If we're talking about feet and pounds, then gravity is 32. Yeah. Yeah. Okay. Anything else? I think just for the time constraints, you're just going to set up the spring problem. Just setting up the spring problem up to the differential equation with the initial conditions. All right. Well, I was going to start doing some examples of things. Okay. So, do you guys want to take a look at the review? We'll get there.
Yeah, so for the undetermined, so, like, should we put like a chart on our notes of when to, like, which function to use, and like, I just don't, can we like go over one with like trig stuff? I don't know.
All right. So let's take a look at undetermined coefficients. Let's start with that, and then we'll jump around, I guess. I'm not even signed in yet. By the way, does anybody have a PDF copy of the book? All right. Because I don't like this system. What? Is that going to be too big? I got a flash drive. I'll give you a flash drive.
Wait a minute. 4.7 is Cañada.
Yeah.
So you.
Oh, sorry. It's not. 4.5 is the part that's not going to be on the test instead of 4.7. So let me make this a little bit clearer here, just so we're all on the same page. So except 4.5, the annihilator method, I did not cover that in class. 4.9 and 4.10. So those are not going to be. So 4.7 is Cauchy-Euler, and that could be on the test. What do you think? Why don't we just do one at a time? Because we're jumping around here all over the place, as it is. All right, so this is page 148 in your book, or 147, I guess. And we don't have to solve through all the problems. We can just set it up and imagine that we can solve the rest of it ourselves. So let's just grab a bunch of them. Undetermined coefficients. They call this the superposition principle. And the whole idea behind this is for non-homogeneous differential equations. We want to find a particular solution for them so that we can couple it up with the original homogeneous part. So let's pick a few of them. Which one should we start with? 7 and 8. Let's do 7. So the tricky part about this is that it's not enough to just look at what the function is on the other side, the non-homogeneous portion. What we need to do is we need to take a look at the general solution to the homogeneous part. They call it the complementary solution. So it's first important to look at what you would get here, because if it all matches what you have on the other side, then you're going to have to add on to the y sub p. I don't know if that made any sense, but let's see. In this case, I can just you should hopefully just be able to eyeball this and imagine that your solutions are going to be complex, right? And if you have a complex conjugate solutions for your auxiliary equation, then your complementary solutions will have sines and cosines. Okay. So if you look at this and you try to solve for m is going to be square root of 3 times the I. And so your complementary solutions will have, well, I think I've been calling them y1 and y2. So y1 is cosine root 3x, and then sine root 3x. So if I look at the right-hand side of that equation, I see that there's no similarities in any of those functions, and so we can move on and just concentrate on this.
When they are similar, what is the exact normally for the y particular you just add numbers?
Yeah.
It's different. What is
Yeah, it's the same. So if you see that there's a cosine here, and then one of our solutions is cosine, then you can just add on another x. Yeah.
Would you do where you add that limit instead?
If it's a Cauchy-Euler equation, so you'll have an x squared in the beginning of your problem. Kyle? Oh, what page is the table? Yeah. Okay. All right. So the book has a table. So y sub p in this case, because there's a polynomial times an exponential function, we need a polynomial, a second order polynomial, and as general as possible. So we can wrap this up in a parentheses. We have ax squared plus bx plus c, and then that's multiplied by e to the 3x. So this should be your y sub p. And so this needs a couple of derivatives. Take two derivatives, and then get this original function, put it into the left-hand side, set it equal to the right-hand side. So the term that would have the x squared e to the 3x will be equal to negative 48, and everything else should be set equal to 0. Okay, so I'll put dot, dot, dot here, and the problem will have, the section will have more information about that. No, it's a derivative of yp, because yp is the one that you're putting in here and showing that your yp will work for this differential equation. No. Oh yeah, that's because you're using the variation of parameters version of this. So you can solve for this differential equation using variation of parameters, but you should know how to do both, just in case I tell you that you have to use. All right. Should we do another one? Somebody requested 8. So let's do 8. With a sine and cosine, it's a little tricky, and so you have to assume that if there's a sine or a cosine there, then the other cosine or sine should be available also. So again, just to make sure, we want to make sure that the general solution for the complementary solution shouldn't have any sines or cosines. So let's check that. So I'm focused on this and imagining my homogeneous solution. So this would be 4m squared minus 4m minus 3 is equal to 0. And I wonder if I can factor that. If not, then we'll just say m is equal to negative b plus or minus the square root of 4. Let's call that 4 squared, so that's 16, minus 4ac all over 2a. Just by looking at it this far, I see a 16, and then this will be a plus. So I'll have, it looks like it won't be 0, my discriminant won't be 0, and my discriminant won't be negative. So I will have 2 real roots here. Okay? And because it's 2 real roots, I can just not worry about that because I'm focused on trying to find a particular solution, and I just want to make sure that I'm not going to have a sine or cosine in there. So what if there is? Then you would just throw in another x.
Like where then? In front of the cosine or the sine?
The one that has the problem?
Well, it has to be in front of both. So wait, let's finish this up, and let's say this is going to be so y1, y2 will not have cosine 2x or sine 2x. So we can just go on and say y2 or yp is equal to, now this is where you would have an a cosine 2x plus b sine 2x. Yeah. So let's see. Can we come up with a differential equation? What if we just assume? So let's just suppose that y1 equals cosine 2x and y2 equals sine 2x. So if we assume that this is the case, then we have to increase the polynomial to the next degree, right? So y sub p is going to be, well, technically it'll be a combination of those things. So it should be ax plus b, and then c times cosine 2x plus d times sine 2x.
If you forget that that is true, like, is there a way you can remind yourself, like, is there a, like, why are we choosing that?
You're just, because you're going from a constant to a linear term, or you're going from a linear to a quadratic, and so you just have to remember your polynomials just grow by a degree, and when it grows by a degree, then you have to That's the only thing I can try to remember. Yeah, it just has to match up with a degree. And if you have a constant times your sine and cosine already, then you have to go to a linear times your sine and cosine. All right? So where is that table?
I don't think that one's in the table either. Yeah.
Actually, the way they wrote their table, it's a little bit more efficient. Or the sine and cosine business. I don't know, it's more efficient. Well, if you multiply it out, it'll be the same. Okay. Yeah. Short answer. You're right, there is no solutions for problem number 1. Good luck with that. All right, we're going to do a spring problem. Okay. Find the equation. So let's try number 11. Uh, 64 pounds stretches a spring by 0.32 or 3/100ths of a foot. Mass is initially released 8 inches above the equilibrium position with a downward velocity of 5 feet per second. So our mass here, before our mass was attached, a spring was at a certain length. And then once we attach the mass, the spring stretched by 0.32 in 3/100ths of a foot, or whatever. Yes, so remember Hooke's, what's Hooke's equation again? K times S. So the force of 64 pounds, and that's already in force, right? So 64 pounds made our spring stretch by 0.32 feet. So your K is whatever your K is. Okay. What is it? And then our mass, we figure out our mass. M divided by G. Is it mg or m divided by g? So the mass is going to be equal to 64 pounds divided by 32 is our gravity. So we got our mass figured out. Does it say, did it talk about a damping force? No damping force. Did it talk about an external force? So that's the initial, but after that there's no external force. So if we had our general equation, which is, what's our general equation? It's m y double prime. Oh, x. M x double prime. And we bring it over plus, was it beta or something? So beta x prime plus kx is equal to an external force in general, but in our problem there's no external force. So in our problem, this is 0, no external force. There's no damping. Which means we have our other two pieces of information, our mass and our K. So we have ourselves a differential equation here. So it'll be 2x double prime plus 200x is equal to 0. So we also have some information about initial stuff. So our spring is going to be hanging from the ceiling, and positive is downward, right? Is that what we established? So gravity was positive. So the mass was initially released at a point 8 inches above the equilibrium. So that sounds like our initial condition, initial position. So what's x of 0? Is it 8 or negative 8?
Negative 8.
Negative 2/3. So one of the things that we need to watch out for is that when we set up our equation, our force is in foot-pounds, and so our measure of distance has to be in feet, and our measure in force is in weight. So this is your initial value and your initial velocity. When they talk about pushing it downward, is that positive or negative?
Positive.
So it's a downward velocity. Remember, our positive downward is positive, so this is going to be a positive. And then this is already in feet, so we're good with that, 5 feet per second. So if we attach those two things here, this becomes, what is it, 4/3? No. 2/3. That's it. from these statements here. Initially released from a point 8 inches above the equilibrium. So that initially released business means it's going to be some sort of position in the beginning. And 8 inches is 8 over 12 because it has to be written in feet. And it's negative because it's above the equilibrium. And then downward velocity means it's going down, so the downward is positive of 5 feet per second. Okay? And this is easy enough to solve, right? Divide by 2, it looks like it's going to be x double prime plus 100, x equals 0. And so this is m squared plus 100. So that's square root of 10, or square root of 100, negative 100. So your m is equal to 10i, plus or minus. So your equation here, this is undamped, so that should be a hint already that it should just be sines and cosines without any exponentials. So your y general x, not a vector, is a function of t. So this is c1 times cosine of 10x t plus or minus 10i. And then just take the derivative and you'll have a couple of equations and a couple of unknowns, C1 and C2, when you put 0 in. And then that should help you solve for C1 and C2. Yeah.
So the homework on problem 3, there was a pretty similar problem, except it was part A and part B. Part A just stated that it was pulled like a meter down below the equilibrium point.
Uh-huh.
You have two unknowns and only one equation because you're starting down at 1. So you said 1 equal to the equation that we find that you had C1, C2, but I couldn't figure out a second equation.
Did you, so the second equation for us came from the derivative. Did you have information about that?
It didn't say anything about the derivative. On the next one, it stated that it was given a velocity, like an initial velocity.
Was that the third one? Okay, so that's 0. That's nothing.
So if it doesn't say, so this one says with a downward velocity of this. If they just say they released it, then there is no initial velocity. Yeah. So
for that, you assume 0.
so you say because it's released, the initial velocity, the starting point is the initial velocity is 0. Yeah. Okay. So if there's no information about a downward or upward velocity like this, then we have to assume that it was released, which means, you know, like dropping a ball. When you drop a ball, the velocity. But they say with a downward velocity. So if they don't follow that up with a downward or upward velocity, then you just have to assume that it's 0. The velocity. This, in this case, yeah, that means they pushed it. So that's the difference between when you're on top of a building, when you drop a ball. When you drop a ball, that's an initial velocity of 0. When you throw the ball down, that has an initial velocity that's not 0. So that's like the same way for these springs. You push it up or you push it down to get things started. If you don't push it, then it'll just be initial velocity 0.
And you won't give us like acceleration, right? You'll just take the velocity, so we don't have to take like second derivative.
Yeah, this is only going to go up to 2 derivatives, not 3. Okay. Any other questions? You want to do another spring problem? With this one didn't have a damping or an external force. We can try to do one with damping and external force. What? Okay, we'll do Green's theorem and we'll come back here.
that one is.
So Green's theorem comes in two different waves. One of them is trying to answer an initial value problem. And then the other one that makes Green's theorem a little bit different is that when you address a boundary value problem. So we could do one or both. Let's try to do like a problem here from number 7. I haven't fully decided yet. So far. Likely be 2 problems, but I don't know yet. So this is Green's theorem, or Green's function. Yeah, let's not worry about that right now. So in these problems, find a general solution for a given differential equation. Use results. Okay, so let's do maybe problem number 10 or something. Arc 10. So for us to be able to create Green's theorem, let's assume that this is an IVP, initial value problem. So let's assume there are some initial conditions. Are there initial conditions? Sorry, let me just take a quick look. Maybe we should do one of these problems down here. Yeah, sorry, I'm going to change problems on you. Let's do one of these problems where we have an actual initial condition, and let's pick 17. So we have Green's theorem. For Green's theorem, we need to find the complementary solutions, so the fundamental solutions for the homogeneous differential equation. So let's start off with that. Let's start off with y double prime plus y is equal to 0. And again, yeah, so you need to have done this a bunch of times. This will have m squared plus 1 is equal to 0, which if you try to solve for will have complex conjugates. And the complex conjugates are 1, plus and minus 1 times I. So m is equal to plus and minus I, which means your general solution, your y1 is going to have a cosine x, and then your y2 is going to be sine x. And then if you do the Wronskian in general, so we need the big Wronskian, which will be cosine x, sine x, and derivative cosine is negative sine x, cosine x. Then this will be cosine squared minus negative sine squared, which will give you 1. So that gives a Wronskian a 1. Now, I think this is a mistake that I saw a lot, maybe not a lot, but enough that I should point it out. It's important that you choose your y1 and your y2 and match that with your w1 and w2. Okay, so if I chose my y1 to be cosine x, then it's this column, the cosine column, that I'm going to replace with the new column. So the new column is going to be a 0, and then it's cosecant x, cotangent x. And then the second one, the one that's not affiliated with a subscript, is going to stay the same. Okay? And then this is going to give us a negative, so 0 minus, and then we have our cosecant x, cotangent x, and sine x, which could probably be simplified a little bit. So we got a negative cotangent x for your W1, and so your U is going to be, well, oh, so you guys have Green's function memorized? Okay. So remember where Green's function came from, right? Green's function came from really the variation of parameters. And if you get W1 and W1, if you look at W1, it's Y2 times f of x with a negative in front of it, right? And that's all divided by W. And then so you just integrate that. So if you don't have Green's function written down or memorized, then you can do it using variation of parameters. It's kind of like the same thing. Yeah?
It's just like jumping ahead. It's just supposed to be, this one put y1 times the negative and 0 f of x times y2.
Yeah. So that's what y2, the negative part. And then the W2 is going to give us the positive part of Green's function. Okay, so if you have Green's function memorized, this is without the integral, right? It's y1 of t, y2 of x. So this is Green's function, and then what we want to do to solve for this is we want to integrate this thing times f of t.
From the initial condition.
The second one?
Yeah.
Okay. So y1 of x, this is all the information we need up here, right? So Green's theorem in our problem is going to be cosine t sine x minus cosine x sine t all over 1. So it turns out to be a nice function. Yeah. Okay, so we have a nice function. We have a nice function to integrate. And remember that your yp is equal to the integral of this thing times what? F of t. Second negative. So we're integrating from pi over 2 in this case to x, right? And the thing we're integrating is cosine t sine x minus cosine x sine t times f of t. What's f of t? So this would be your answer. Yeah. Well, it depends. If the instructions say don't, it says evaluate the integral. So I probably won't have you evaluate the integral. Well, some of the problems you'll evaluate the integral. So this would be your Green's function times f of t. Yeah.
And the lower limit is, so the two, so are those always be the same?
For initial value problems, these numbers will always be the same. For
This will only work for initial value, or the initial value with two of the same.
yeah, so that's what initial value means. The x values or the t values here are the same, and then one of them is the original function. The other one's the first derivative. The other one is a boundary value problem, where it'll be different. Yeah. Yeah. Yeah, so it could be y of something equals something and then y of something different, or y prime.
Then it would be the other one where we split it up and we have like two different integrals.
Uh-huh.
Okay.
Yeah. For the general solution, the y1 and the y2 will actually be taken into account here already. So you don't need to do that, because the Green's function is taking care of the coefficients for this as well. So you don't have to take care of that anymore. Yeah. Oh yeah, if you don't have the initial conditions, then that's needed. So that would be a boundary value problem. Well, it depends. If the problem's asking you to use Green's function, then you should use Green's function. So for this one, if you notice, the inputs are different, like 0 and 1, or 1 and... oh, that's complicated. We won't worry about that one. Oh, we don't have an actual problem here. I mean, we could try to solve for it and reason through it, but let's actually.
Is the piecewise one the one where you have to make sure your y1 corresponds? Remember we did one where we flipped it because we needed y1 to be different. So we had to check to make sure that our y1 was actually that, and then we needed it. If not, then we would flip it.
I don't know.
Let me see if I can find it.
I think we did number 41 in class, didn't we?
Yeah, we did.
Yeah. Let's do 39. Okay. So it's like the other one. We have to set this up by finding the homogeneous. So this looks very similar, right? Are we used to this now? So y1 is equal to cosine x, y2 is equal to sine x. With the boundary conditions, we are kind of and for us to be able to use Green's theorem, notice that the boundary conditions are all equal to 0. So that's another important piece of information. this is 4, 8. Yeah. All right. So what do we need to do? We need to find Green's theorem. First, we need to find the Wronskian. The Wronskian is 1, right? It's the same thing. I think we need to do something else here. I think we need to take double check our initial conditions to make sure that our complementary solution is going to satisfy the initial condition. Yeah. So we have to check y1 and y2. So y1 of 0, cosine of 0, unfortunately does not equal a 0, right? y1 of 1 is cosine of 1, which also does not equal a 0. y2 of 0 is equal to 0, or it's equal to sine of 0, which is 0. So I think because of this fact over here, because the cosine of 0 does not equal to 0, and the sine of 0 does equal to 0, I think we're going to want to have sine to be your y1 in this case.
That would make
Our C1, yeah. So what we're going to do is we're going to switch this little check over here.
But then when we do y1 equals C1 also has to.
No, I think you said it backward. I think C2 has to be equal to 0, and C1 won't be, because this will make it. Well, no, that we're switching it now. So by switching it, we're going to. So we want to make sure that we're able to satisfy the initial conditions with at least one of our general solutions. Well, no, the second one would satisfy the homogeneous differential equation, but we still need those two to construct our Green's theorem to find a particular solution. But in doing so, we need to check which one of these. If both of them satisfy the initial conditions, then we're all good. But if only one of them satisfies them, we have to make sure that we place that in the first y1.
Why does doing that make a difference?
Because when we integrate the first one with respect to the first one, we're going to integrate from our first endpoint to x, and then we're going to integrate our second endpoint to b, which in this case is 1. And so we want the y1 to satisfy that differential equation. Yeah?
More than like y1, y2, y3, y3
Yes. So whatever satisfies the first one, but we won't have. Yeah. All right. So we need our Green's function. Do we have information about Green's function? By the way, if we do the Wronskian, if I switch these two around and we do the Wronskian, what do you think I'm going to get? Am I still going to get 1? You're going to get -1. So the Wronskian in this case is equal to -1. So make sure that we remember that this is negative. All right, so Green's theorem changes now into a piecewise function. The first piece will have y1 of x, or is it t? y1 of t. So the first one goes from 0 to x, and the second one goes from x to 1, and that's based on our boundaries. So y1 of t is cosine t, y2 is sine. I'm sorry, I switched them here. So y1 is sine now. So this is sine t cosine x over negative 1. So let's just put a minus sign in front of that. And then y1 of x, so sine x cosine t, and then divided by negative 1. F of t this time is 1. So f of t, they usually, in their notation, they don't do that until they integrate. So this is just Green's function. And then to actually find the solution, they would integrate this. And technically, it's the integral of the whole thing from 0 to 1 with the x's in the middle, but they decide to split that up because this is, in fact, a piecewise function. So the split up is going to go from 0 to x for the first function, minus sine t cosine t. So that's the g. Sorry, sine t cosine x. And then the f function is 1 dt. And then we integrate from x to 1, the upper limit, minus sine x cosine t, again, times f dt. By the way, if you do the variation of parameters, you'll see that this sine x and this cosine x can be thought of as constants, so we move it outside. So that's really y1 and y2. And then this inside part is the u, and we're integrating it, or the inside part is u prime, and we're integrating it to get u. And so this really just makes a compact way of doing the variation of parameters. Okay. Yeah. Because I want to satisfy the first one, the y of 0 is equal to 0. That has to work with this integral going from 0 to x. And so this is your first one. And so your first function has to satisfy that. And so this is the first function that you're going to use. The order turns out to be important. Yeah? Yeah. I mean, if it's a solution to an initial value problem, it's the same thing, right? So I guess we can call this y as well. But it's a particular solution to an initial condition, so it's also the same thing. And what this means is that we don't consider the complementary solution anymore. We don't need to take a look at that. It's kind of built in. When we evaluate at the limits, it's kind of built in. So, all right. I think we have 3 minutes. Oh,
Can we still do E instead?
Yeah.
Just do it?
what?
Look at them.
The one with the damping? Well, the only thing about the damping is that they'll just say with a damping coefficient that is numerically equal to.
What they give you just the number? So we set the equation. 0.8, right?
Like number 31? So a mass 1 slug when attached to a spring stretches 2 feet and then comes to a rest in the equilibrium position. Starting at t is equal to 0, an external force is applied to the system. Find the equation of motion if the surrounding medium offers a damping force that's numerically equal to 8 times the instantaneous velocity. So if we go back to our mx double prime plus beta x prime plus k, x is equal to f. We have our f. We have our mass is a slug. We have a damping force that's numerically equal to 8 times the instantaneous velocity. And a spring stretched to 2 feet. So this one is already in feet. We're looking for the spring constant. And with 1 slug, what's the force of 1 slug? 32, right? Is that right? 32 pounds. 1 slug is 32 pounds. So K is equal to what? 16. So here's your differential equation. And starting at T is equal to 0, an external force is applied to the system. So technically, the external force applied to the system, oops, this is 0. It begins pushing with this external force. So if it was at rest, well, the external force is given by this. So you need to put 0 into this, which is, in this case, going to be 0 anyways. Okay, so our initial position is 0, and our initial velocity. Do they start at equilibrium? Yeah, so starting at rest. So this should be your differential equation, and this is your initial conditions, and then you can solve for it. Okay? All right, so good luck on your test.
You won't do any marking for the period or like the
No, I'm not going to combine it.
So the giant